Okay, let me remind briefly what we have derived on Monday. So we considered free electron gas, and then we add the Coulomb interaction. To be more specific of model in the metal we have crystalline lattice of atoms. However, if we consider alkali metals, for example, like lithium, it contains one s electron in the shell. So this electron is collectivized into the band. The band is characterized by parabolic dispersion at the bottom, which is a good approximation, so we consider free electrons. But since each atom gives one electron into conduction band, we have therefore the same amount of ions. So atoms are neutral, electrons are negatively charged, therefore ions are positive charged. So in total, our system is completely neutral. So there is a neutrality of the system. And we consider these electrons being subject to Coulomb interaction, because electrons are charged particles. We consider the Coulomb interaction using perturbation theory, assuming that the validity of perturbation theory is justified by high density limit. Namely, in the limit of Fermi momentum A, B, much larger 1, where I remind you, I use units that h bar is equal to 1. In principle, I should write kf A, and bore radius AB is h squared over ME squared. So this is the limit, and of course, if h bar is equal to 1, I don't discriminate between k and p. This is a high density limit, and as long as this limit is fulfilled, it is legitimate to consider Coulomb interaction as a perturbation. So we derived the dielectric function epsilon as a function of q and omega, so momentum and a frequency, and it is written as 1 plus 4p e squared divided by q squared, and here we have sum over k sigma, n k sigma minus n k minus q sigma divided by omega plus epsilon k minus q minus epsilon k. So please be careful here. Epsilon is a dispersion, and curly epsilon is the dielectric function. So don't confuse two notations. Sorry, historically we used to use these letters, and if I will use another notation for dielectric function, you will get great confusion in the literature. So we said that we define polarizability, namely this function with a sign minus is minus p q omega, and therefore p q omega, I will rewrite it again, because today for whole lecture we will be dealing with the discussion of properties either of this polarizability, or sometimes it's called polarization operator. It's equal, as I said, minus sum over k sigma. I will rewrite it n k sigma minus n k minus q sigma divided by omega plus epsilon k minus q minus epsilon k. And in principle, I said that this is a complex function of its argument. And in principle, in order to be absolutely precise, if I define this function as a retarded function, I need to write here I delta, and then this function doesn't have any poles in the upper half plane of omega. The origin of this small addition, so delta goes to 0, has been discussed during the last lecture. But the point is that this function has both real and imaginary part. Today, for whole purposes of my lecture, I will be considering only a real part of this polarization operator or polarizability. So, let's start properties of this, of epsilon as a function of q omega. We start with the obvious properties, then we come to less obvious properties, and then we come to not obvious properties at all. So whole today's lecture is devoted to discussion of either epsilon or p. So first properties of epsilon. Let's take limit omega goes to infinity. You see, if omega goes to infinity, this term is gone, so polarization goes to 0, and therefore epsilon q omega goes to infinity is approaching 1. What does it mean? High frequency means small times, because in quantum mechanics, for example, you have uncertainty delta time delta E, which is always bigger or greater to h bar. When you take a Fourier transform, so you multiply to exponent e to the power I omega t, so characteristic times are of the order of 1 over omega. So if omega goes to infinity, it means you consider correlation function at very small time. So if times are small, omega goes to infinity, polarization or dielectric function approaches 1, so there is no time for screening, times are small. So this is obvious property with obvious meaning. Second property, if I take a limit q goes to infinity in my dielectric function, so I remind you that epsilon dispersion p is p squared over 2.
Excuse me, sir.
Sorry?
Yes, the first property. Do you say there is no screening, no time screening?
There is no screening at very small times. Screening takes some time. If you take a momentary process, no screening. Okay?
Okay.
So, let me continue.
You can continue.
Okay, so this is my dispersion spectrum. You see here, we have epsilon k minus q, and here there is epsilon k. If I take q very large, which means here I have q squared over 2m, epsilon goes to infinity, and therefore the electric function q goes to infinity. Omega also goes to 1. But with the same reasoning, like in quantum mechanics, we have delta x, delta p uncertainty, which says it's also greater or equal than h bar. In taking Fourier transform, multiplying by iqr, you see that characteristic q's are of the 1 over r. If q goes to infinity, it means you should take very short distances of your metal properties. So there is no screening at short distances as well. Screening occurs at some distances, which we are going to derive and discuss at the very, at the very end of this lecture. But these are two obvious properties. Let's now discuss the properties of dielectric function in two limits, namely omega goes to 0, q goes to 0, but we discuss it in two possibilities. We first of all consider limit when omega is not 0, but q goes to 0. This is one possible limit. And second limit, when we first put omega equal to 0, and then consider q being small. Although it sounds a bit silly, you will see that these two limits are not commutable. And the reason for non-commuting properties are deeply in the properties of many-body harmonic system. And you will get different result depending on which variable you put first, omega or q. And again, it's not surprising. You will see many examples, several examples during this course. In particular, the thermodynamic limit, for example, when you take a number of particles goes to infinity and volume goes to infinity, but their ratio in density is constant, the thermodynamic limit and limit taken interaction to infinity are also not commuting in many cases. So you are not, it depends which property you define, and we will see clearly that defining different limit assumes two completely different properties of the method. So, as a number 3, I will be considering limit q and omega being small. Q and omega being small. And we will see what does it mean small. And in principle, to be more pedantic, I consider limit omega goes to 0, q goes to 0, but also q of omega goes to 0. So q goes to 0 faster than omega. Okay, let's start with discussing polarization operators. So P, since I'm interested in real part of P, from now on I will remove I delta and I will remove index R. Q omega is equal to minus. Let me write these two terms separately. K sigma and K. Let me take this expression and take one of the omega out of bracket. K sigma, K minus Q sigma, divided by 1 plus epsilon K minus Q minus epsilon K divided by 1. Okay? You see that what I did, I divided numerator and denominator by omega, and there is no approximation anymore. But since I'm going to take this limit, I can expand my denominator in terms of this function, which in this limit considered to be small. This is legitimate expansion, Taylor expansion. So this is minus 1 of omega, sum over K sigma. I have N K sigma minus N K minus Q sigma. And here I have 1 minus epsilon K minus Q minus epsilon K divided by 1. So I keep only first term in the Taylor expansion of this rational function. Okay? Let's now see. The first term, when I multiply this bracket by 1, gives me 0. Why? Because I just have a difference of two Fermi distribution functions. I remind you that nk is a Fermi distribution function, e to the power epsilon k minus mu divided by temperature plus 1. And for the most of the properties of my today discussion, I will consider temperature equal to 0. Therefore, Fermi distribution function is a step function. So this is n epsilon epsilon. Okay? So the first term gives me 0 because in this sum, considering term nk and ak minus q, I can change variables, define new variables k minus q, and these two functions exactly cancel each other. So what remains is minus 1 over omega squared, and I have sum over k sigma, n k sigma minus n k minus q sigma, multiplied by epsilon k minus q minus epsilon k. Also, I will consider situation with zero magnetic field, so I don't assume that degeneracy associated with the spin projection is lifted. So the situation is degenerate. So now this is the equation which I'm going to evaluate, and in order to do, I will do the same procedure as before, namely, I will take continuous limit and replace summation by integration. And by doing this, in order not to keep my volume everywhere and take care that volume is correctly cancelled out in the left and right hand side, which I did in all previous 4 lectures, I will also assume that all calculations what I do, so this is temperature 0, magnetic field equal to 0, and I consider volume equal to 1. So I compute all quantities per unit volume. Okay?
Professor?
Yes?
So I have a question about how you get to the last term. I mean, you said the first term of the previous one is 0 because you take the temperature goes to 0, right?
The first term is epsilon nk sigma minus nk minus q sigma, right? So this is sum over k sigma nk sigma minus sum over k nk minus q sigma. In this term, I will take a new variable. This is summation over all possible k's, 3-dimensional states. I will denote k minus q as whatever you like, p, and then I have a summation of all p and np. So you see that k is a summation index, p is a summation index. This term are equal to each other. I make a shift of variable, and that's it.
Oh, so it's just a shift, not because of the temperature goes to 0.
No. It's a shift, and this is correct for any temperature. So just to be careful with sign, let me say that I'm considering minus p. Therefore, it would be plus 1 over omega. Here it is plus 1 over omega, and here it is minus 1 over omega squared. So this is the quantity which I'm going to compute on the left part of the blackboard. Okay. I need to do some preparation for this computation. Namely, I need to see and expand this term and this term in terms of small q. And in principle, the calculations which I do for this limit small q small omega are not necessarily related to parabolic dispersion. I said that for most of what I'm doing, I will consider p squared over 2m, but in principle, it's equally applicable for time binding model. I can specify my dispersion at the very last moment. So epsilon k minus q is equal to small q. You see, I do Taylor expansion, epsilon k plus d epsilon k over d k times minus q plus and so on and so forth. So the derivative of your spectrum with respect to your wave vector momentum or quasi-momentum, this is a group velocity. So this is plus dk, your group velocity. So therefore, this is equal to epsilon k minus vk scalar product q plus and so on and so forth. I do the Taylor expansion and keep only lowest term with a small q. So nk minus q is equal to nk plus dnk over d epsilon k times d epsilon k over dk times minus q. Therefore, I have derivative of the Fermi distribution function with respect to energy, and I have the same Vk times q. Therefore, I continue here my minus pi q omega is equal to minus 1 over omega squared sum over k sigma. So I have nk minus dnk over d epsilon k times dkq minus nk. This is the first term. I will put sigma. Sigma. The second term, it's epsilon k minus vk times q minus epsilon k. So therefore, it is equal to minus. Now I assume that my spin index corresponds to characterization of the degenerate state. Therefore, I take summation of a spin explicitly, minus 1 over 2 over omega squared, sum over k. I have minus. Sorry, let me see that I did not make any mistake. Epsilon k minus q. Epsilon k minus q. Aha. This is minus, this is plus, and this is plus, because I have epsilon nk minus nk plus q. So, therefore, I'm considering overall sign. The overall sign is going to be plus, because we have a minus, plus, minus. However, I would like to keep a minus, so this is minus dn over d epsilon k times vk scalar product q squared. Good. So this is how I simplified my equation. So let's proceed further. Okay? So this is Fermi distribution function and epsilon divided as a function of epsilon. So this is Fermi energy, this is 1, 0. I need to compute the derivative of the Fermi distribution function with respect to energy. So let me first put it pictorially that this is like this. It's the function, Fermi energy. So this is minus dn over d energy, function of energy. And let's indeed see that this is the case. Let's take a derivative of the Fermi distribution function with respect to energy. So this is Fermi distribution function is 1 divided by e to the power epsilon minus mu over temperature plus 1. So this is the minus. I'm taking derivative e to the power epsilon minus mu over temperature plus 1 squared times exponent e to the power minus epsilon minus mu over temperature times 1 over temperature. So let me take out epsilon e to the power epsilon minus mu over 2 temperature out of the bracket. So what I have here is e to the power mu minus, sorry, epsilon minus mu over temperature divided by e to the power epsilon minus mu over temperature, e to the power epsilon minus mu over temperature plus e to the power epsilon minus mu with sign minus over temperature squared. There is minus and there is 1 over temperature. So this term cancels out. So minus dN over d energy is equal to 1 over 4 temperature, 1 over cosh squared epsilon minus mu over 2 temperature. So you see that this is 1 over cosh hyperbolicus. It has this shape, namely if epsilon is large, there are exponential tails, and when epsilon is equal to mu, it approaches 1 over 4 temperatures, but then in the limit of temperature goes to 0. This is a 1 over limiting case for the delta function. So this is why this integral is going to be very simple in the limit temperature goes to 0. And this is the way how people compute integrals with a Fermi distribution function at finite temperature. And this is what you are going to do on a tutorial on Friday with Andrei. Today I showed you some examples. There is a factor of 2 here. Okay. So what is important is that temperature equal to 0. This is delta function epsilon minus epsilon. So minus p as a function of q and omega is equal to now minus 2 over omega squared. Now I replace my summation by integration. So this is integral over dk over 2 pi cube. It's minus dn over d epsilon k times dk times q squared. And as I said, I consider volume equal to 1 in order not to bother on keeping volume in my expressions. So in a standard way, as I said, this is delta function epsilon minus epsilon. So I need to come from integration over k to integration over energy. So this is minus 2 over omega squared. Let me see that I did not forget sign. So I come to spherical coordinate system. This is k squared dk. Everything is isotropic so far here, but not isotropic here, of course. 2 pi cube. Now I have integral from 0 to pi sinus theta d theta. I come to the spherical coordinate system and integral from 0 to 2 pi d pi. So what then remains times the scalar product is vk squared times q squared times cosine squared theta. Nothing depends on phi, and then I have delta function epsilon minus epsilon. Okay.
I want to ask about the derivative of n with respect to E. Okay. The delta function, I thought is at the point where we have the Fermi energy, but in the Dirac expression you wrote, there is no reference to Fermi energy.
There is a chemical potential, and at 0 temperature, chemical potential is equal to Fermi energy. You see that I put mu here, but mu at temperature equal to 0 is equal to Fermi energy. And I do my calculations at 0 temperature. At zero temperature, this quantity diverges as one over temperature, as it should be. So everywhere except epsilon equal to Fermi energy, this is zero. However, because exponent decays faster than the A power law, but only at epsilon equal to epsilon Fermi, where cosine square is equal to 1, we have the derivative equal to infinity. And this is precisely how delta function behaves. You can check all other properties of delta function, that the integral over this function at finite temperature will give you 1. So this is yet another property of delta function. But as I said, for real finite temperature, you need to use this expression. However, for temperature equal to 0, the limiting function is delta function epsilon minus mu, but mu at 0 temperature is a Fermi energy. Okay?
Okay.
So, as usual, nothing depends on phi. So this integral gives me 2 pi. The integration over angle theta is done in a very straightforward way. Namely, I denote cosine theta as x. So this is d cosine theta, d minus cosine theta. So if I define a variable x is equal to cosine theta, what I get here is minus 2 over omega squared integral k squared dk divided by 2 pi cube. I have a 2 pi from integration over d phi. I have integral from minus 1 to 1 dx vk squared q squared times x squared times delta function epsilon minus epsilon k. So, first of all, I'm dealing with very small q, which means I'm dealing with excitations which are well defined in the vicinity Fermi surface. So without any loss of generality, I can replace Vk squared by Vf squared. So this is minus 2 over omega squared times 2 pi divided by 2 pi cube. The integral over, so I have q squared, Fermi energy, Fermi velocity squared from here, because the integral doesn't depend on q. Integration over x squared dx gives me x cubed over 3. In the limits 1 and minus 1, it gives me 2/3. And I have remaining integral.
Sorry? Here you replaced cosine theta by x, but we have also sine theta. Right?
Yeah, but this is dx. Sine theta d theta is minus d cosine theta, so this is dx.
Oh.
The limits will be from 1 to minus 1, so actually it will be minus dx, but limits are from 1 to minus 1, are remote limits, and therefore this is dx. This is a very standard way, integration of a solid angle. We will do it on almost each and every lecture. So what remains is integral k squared dk delta epsilon minus epsilon n. Okay, I'm almost done. This integral, remaining one-dimensional integral, can be calculated by transferring from the momentum to the energy variables. I can do it with the density of states, of course, but I can also do it explicitly. So let me collect all terms. So minus pi q omega is equal to minus 2 over omega squared. I have 2 pi divided by 2 pi cube. I have 2/3. I have Vf squared q squared, right? And then I have integrals from 0 to Fermi energy. And in usual way, so k squared over 2m is equal to energy. K, therefore, k is equal to 2 square root over 2m energy. Therefore, I have a mass times square root over 2m energy times delta function epsilon minus epsilon f d energy. So you see that this integral can be simply computed. Integral with the delta function is just equal to the function which stands in front of the delta function at the zero of delta function. So therefore, this integral gives me m times pf, Fermi momentum, nothing else. So let me now cancel out all factors. So 2, and 8 cancels out. Pi and pi squared cancels out. Pi and pi cube, so pi cube gives me pi squared. So there is 3 omega squared. I have m pf divided by pi squared. And I have bf squared times q squared.
Hello, Professor.
Yeah.
So,
Yeah.
what was your argument for replacing Vk with Vf before?
As I said, I'm dealing with a Fermi sphere. So I'm computing my integrals very close to the Fermi surface. Therefore, the group velocity at the Fermi surface is equal to Fermi energy. We discussed this as a spectrum. So this is the group velocity, and this is a constant equal to Fermi energy. It doesn't depend on k, because we are seeking this integral, by the way, force us to sit on the Fermi surface. Okay? Because this is the modulus of the group velocity depending on factor k at k and typical k, not typical, at zero temperature k is precisely equal to kf. Therefore, this is df.
As I have another question about the delta function. I mean, how do you get it from the cosine hyperbolic?
Check the properties. As I said, the delta function or Dirac delta function is defined as a function which is equal to 0 everywhere except a singular point x equal to x naught. And the integral of a delta function over all x gives you 1. So this is exact function at final temperature. I'm arguing that at 0 temperature, this is a delta function. First of all, I check that at 0 temperature, this function is equal to infinity everywhere except epsilon equal to epsilon f. What remains to be checked that the integral over this function is equal to 1. I leave it to you for exercise. Or take a textbook where the delta function can be limited and approximated with some functions. In particular, one of typical way to have a limiting function for delta function is Lorentz function. We will discuss it many times in the chapter 4. Another way to do delta function is to approximate it by Gaussian function. This is the approximation. I'm not going to prove your theorems. I'm just arguing to common sense that I tested and I checked the most obvious properties, that this function is 0 everywhere except Fermi energy, but equal to infinity at this point. At final temperature, it actually forms the Gaussian shape peak, and you can check that the integral over this function over all range of energies gives you 1. Okay, let's go further. So I got this nice expression. Now I'm ready to come to the proper thing. Number 2. You know, the only way to understand how it works is to exercise yourself. At the end of this lecture, I give you a few exercises. So by doing this exercise, this is not philosophy, this is physics. And one of the ways, and maybe the only proper way to learn how to compute in modern theoretical physics is learning it by doing. So you need to practicize yourself. Okay, I'm plugging in everything here. So property number 4, property number 3. Epsilon, so epsilon, curly epsilon, q omega is equal to 1 plus 4 pi e squared over q squared. So this function, you remember, is minus polarization operator. Minus polarization operator gives me minus. So I put minus here. I have MPF over pi squared times q squared VF squared over 3 omega squared. Good. And you see that q cancels out. So in this limit, the dielectric function doesn't depend on a small q, because singularity associated with the Coulomb interaction cancels out small q expansion, and this is precisely limit when q goes to 0 faster than omega. So therefore, this is 1 minus, I will write it, omega p squared, pl squared divided by omega squared, where omega plasmon squared is equal to 4 pi. Let me multiply it by m squared and divide it by m squared. So I have m pf cube divided by pi squared, 3 pi squared times m squared. So this is everything what I collected in front of 1 of omega squared. So mass cancels out, but you remember that pf cube is equal to 3 pi squared n over d density. So therefore, plasmon frequency squared is equal to 3 pi is cancelled. So this is 4 pi e squared. E squared density of electrons divided by m. In the limit of small omega, the electric function diverges at 1 over omega squared. This is a typical response. And we obtain that for omega smaller than omega plasmon, the dielectric function is negative. And for omega larger than omega plasmon, dielectric function is positive. The change of the sign of dielectric function occurs in the visible spectrum. You know, in the temperature of our spectrum, in the range of what I'm saying, that we have colors associated to a certain frequency, right? This is how I accommodate the color. The visible range of frequencies recalculated in kelvins, as I said, I need to take h bar into account, k Boltzmann into account, is between 3,500 and 6,500 Kelvin. This is the range of frequencies which we see by our open eye. And each color corresponds to each own frequency. So the change of the color will also change the reflection indexes, which is associated with the imaginary part of a dielectric function. And this is actually related to color of the metals, and this is also explains why metals are shiny, because they change their dielectric property at omega corresponding to visible part of the spectrum. But we said that our effective interaction as function of q omega is equal to V node as a function of q, bare Coulomb interaction divided by epsilon q omega. So you see that zeros of the dielectric function, so this is omega square minus omega t square divided by omega square. So I can write it as omega square dq divided by omega square minus v t square. So the poles of effective interaction define me the quasi-particles or excitations in my model. So what I see that the excitations are plasmons. These are excitations which are gapped in three-dimensional metal and characterized by the gap equal to plasmon frequency. And in order to be sure that my excitations for quasi-particles are well defined, I need to calculate the lifetime or inverse lifetime of these quasi-particles, and I leave this exercise to you. What you need to do is to add I delta. Sorry?
Sorry, Professor. I lost off track of where you are because you were going too fast just now.
I computed the dielectric function as a function of q and omega in the limit q goes to 0 and omega to 0. I obtained this shape of the wave function. You agree?
Professor?
Yes.
How would you get that? I'm lost on how you get omega p prime square. Is that n electron or something else? No, down?
Sorry. Do you agree with this line, which I used 10 minutes to compute?
Yes.
This line. Omega plasmon is computed as a coefficient in front of the 1 minus omega square. I did calculation, I obtained this expression. It is final.
Actually, I have a question about the definition of the omega plasmon. Where does the m squared in the denominator come from?
Because I have a Fermi velocity square. I multiply by m square and divide by m square. M times Fermi velocity is equal to Fermi momentum. So this is why I got Fermi momentum times Fermi momentum squared. This is Fermi momentum cubed.
Then is that n electron in the omega p prime? Down the Venn expression.
M over V. This is number of electrons per unit volume. This is by the definition n electron. This comes from the connection between the Fermi momentum and density of electrons, which I derived on my second lecture.
Okay, so I think I know where I missed the so from the definition of omega plasmon and to what you talk about the V effective, I don't really understand. So what is V effective?
This is what we said at the very end of last lecture. So my effective interaction is equal to Coulomb interaction divided by the dielectric function as a function of q and omega. This is one of the definitions of the dielectric function. You remember, this is associated with a rho external response to rho external and rho induced. So it's rho external divided by rho total, but this is actually the physical implementation of the definition of the dielectric function. So my effective interaction is equal to bare interaction divided by the dielectric function. And this is what I thought from very beginning, that it's q equal to 0, q omega goes to infinity, or q goes to infinity, omega goes to infinity, the dielectric function equal to 1, and therefore my effective interaction is equal to bare interaction. Just 4 pi e square over q square, so there is no time for screening and there is no space for screening. for short distances and for small times. But now I plug in more sophisticated expression for the dielectric function, computed in the limit where both q and omega are not equal to 0, but being small. So this is what I got. I plug it in here, and I got this shape. Do you agree with me?
Yes, yes.
Then we come to this point more and more. That if we define some correlation function, and this effective interaction, in some sense, can be identified with a certain physically observable correlation function, then we are saying that poles of this correlation function define the range of excitations, so the quasi-particles are associated with the pole of this correlation function, but imaginary part, so the position of pole in the complex plane tells us about the lifetime. As I said, the excitations are plasmons. They're characterized by gap, the plasmonic frequency. So your excitations, if we are talking about spectrum, are gapped. So this is omega as a function of q. This is omega plasmon, and this is q. So this is plasmonic range. So first of all, there is a gap. Second, you can do calculations and be bit better and compute that it behaves in the vicinity of gap as a q squared. But as long as you consider long wave limit, namely q goes to 0, this is what we are doing, the most important part is that these excitations are gapped. The excitations in the Fermi gas are not gapped. The excitations in weakly not interacting Bose gas, as we see it on Monday, are not gapped. These are sound waves. The phonons, the excitations associated with the vibration of atoms, have two different branches. First of all, there are acoustic phonons. You discuss it in the course of electrons and phonons and solids. The acoustic phonons are gapless excitations, but there are also optical phonons. The optical phonons are gapless excitations. And then you consider how gapless and gapless excitations contribute to thermodynamics. At least I believe you did it. Here we have plasmons. The excitations associated with the fluctuations of the density of charge. Electrons are charged. And we discovered that plasmons, so these excitations, are characterized by the gap, which are plasmon frequency, which is plasmon frequency. The excitations are well defined when the energy of excitation, and energy of excitation is precisely plasmon frequency, is much larger compared to the inverse lifetime of these quasi-particles. We discussed it, and Friday Andrei is going to rediscuss it, how the lifetime of fermions is behaving in the vicinity of Fermi surface. But I gave you some quantitative arguments saying that closer we to the Fermi surface, the better quasi-particles are defined. We are dealing with a 2- or 3-dimensional Fermi gas. In 1-dimensional, it doesn't work. For plasmons, we already computed the energy of quasi-particles. Computation of a lifetime will take me another 40 minutes. But as an exercise, I suggest you to do it. In order to do it, you need to compute the imaginary part of this function. And I give you a hint that 1/tau inverse lifetime is proportional to e to the power minus m omega plasmon squared divided by 2t. If you consider temperature not sufficiently low, so you see that the inverse lifetime is exponentially small. Temperature is much smaller than the plasmon frequency. It is also bounded from below, but let's not discuss this. So for some low temperatures, inverse lifetime is exponentially small. This is, by the way, called Landau damping. And therefore, plasmons are very well defined quasi-particles. associated with fluctuation of the charge density of the charge. Okay? Where are you lost? Are you okay now?
I'm still not sure, but maybe I will try later, because I don't really understand when you mention the quasi-particle and about the poles, I think, because yeah.
Because as I said, we will come to this point again. If you compute the correlation function, and most of our course is going to be about computation of correlation function. In particular, these computations which we did, and I show you more solid grounds later, are associated with the density correlation function. So this polarization operator, so to say, is related to density correlation function. Namely, you have your density at point R t, you have your density operator at point R prime t prime, and you take average. So this is actually function which I computed. In order to show that this is precisely one-to-one correspondence, the easiest way is to go to green function format. I will come to more detailed explanation why it is so late. Then, if we discuss density correlation function in the Q omega representation, we see that this density function has certain analytical structure. Namely, it has pole structure. Whenever you have poles, you can say that you have excitations in your system. For example, these free electrons can also be considered as pole as a sort of certain correlation function. Namely, you take psi, your wave function, as point RT, you take psi Dielectric operator as a function R prime T prime, and you take average. So this is single particle correlation function. This is four particle correlation function because it's psi prime, psi prime. Single particle, two particle correlation function. Pole of this function defines me electrons and holes as elementary excitations in the Fermi liquid. In a two particle correlation function, or certain susceptibility, we have another branch of many body excitations. So here we are talking about true many body physics. So as well as phonons, because phonons are collective oscillation or collective excitation associated not with the vibration of a single atom, but with the vibration of a whole lattice. Here we have fluctuations of the density of the charge, and therefore there are certain excitations like the phonons associated with the fluctuations of the charge. Phonons are related to neutral lattice displacement, and therefore you have Goldstone theorem, you break certain continuous symmetry, and as a result you have a gapless branch of excitations. I hope you had a time to discuss either in statistical physics or electrons in the form. So what does it mean, Goldstone modes? Did you? Do you know what's Goldstone theorem? If you don't, we will start with this.
No. The Goldstone? No.
This,
we haven't studied Goldstone, I think.
This is very important concept, which is based on the symmetry concept. You break down certain symmetry, and we will see in details how it happens with a weakly interacting Bose gas. So where you see how this Goldstone theorem works and what are necessary and sufficient conditions for existence of the gapless excitations, namely Goldstone. In the crystal, you break certain continuous symmetry, and therefore you have a Goldstone. These are acoustic forms, but of course you have a Brillouin zone, and therefore you also have gapped excitations, which are optic forms. In the charge system, even in a continuous limit, because one of the conditions of Goldstone theorem, namely short-range interaction, is broken, you don't have those tone modes. You have gapped excitation. In a sense, they're equivalent to optical phonons. These are gapped excitations, and you can treat them as gapped excitation. And therefore, you can discuss whole thermodynamics associated with the plasmons. These are true excitations in the system, and you can also discuss lifetime of these quasiparticles. Excitations and quasiparticles are synonymous. But you see, the point which I make very clear, that it is not the dielectric function which is that observable, which results in pole structure and excitations. This is inverse dielectric function, which is true correlation function, which is responsible for their calculation. This is very delicate moment, by the way. And I remember that 20 years ago, when the high TC, high temperature superconductivity, was discussed, many people didn't understand what is true correlation function to be measured. Either it's dielectric function or inverse dielectric function. You see that this is inverse dielectric function. So this is not poles of it, but zeros of dielectric function, which define as the branch of collective excitations. Okay, think about it. I promise you that we are going to have tough lectures, but I have like half an hour less in order to derive the last limit which I need, namely the limit where omega is equal to 0 from very beginning, but Q is. So the last limit for my calculations, and I'm afraid that I spent some time for very important discussion, because I need you to understand what's going on. In all your previous courses, you did something else, but this is a course of many-body theory. And many-body theory, it's not like just statistical physics or quantum mechanics, thermodynamics, whatever. It's mixture of everything. And in particular, in order to show you how many-body methods work, I computed this dielectric response. So the last limit, limit number 4, is epsilon q omega taken in the limit q goes to 0. Omega goes to 0, but omega over q goes to 0. So omega goes to 0 faster. Please compare with this. And therefore, I'm allowed, since omega goes to 0 faster than q, I'm allowed to put omega equal to 0 from very beginning. This is what I do. Okay? So, static polarization or static polarizability, so this is Q0, I take minus in front, is equal to, I take summation over sigma, so this is 2 integral over dk over 2 pi cube nk minus q divided by epsilon k minus q minus epsilon k. So this is a static taken at omega to 0. Here I'm not going to Taylor expand, I'm going to calculate this function exactly. So this is a difference with the way I compute it before. Now I'm going to sketch you exact calculation of this function, which is known as Linhart function. So this is Linhart function. Unfortunately, since I spent a lot of time for discussion, I will not be able to proceed with each and every calculation step, but I will sketch some details of the calculation. Again, no approximation, except I take temperature equal to 0. So, as a first step, being exact, I will write these two terms. And first term, this one, and second term is this one, coming with sign minus. I keep first term intact, and in the second term, I will make a replacement. So this is second term. I will have replacement k minus q is equal to minus k prime. I do it because I use that my dispersion is symmetric with respect to k to minus k. And actually, since my distribution function depends on the spectrum, it also possesses this symmetry. I see that the second term, which comes with a sign minus, after this replacement, will produce the same structure as the first term, so they sum up. So this is therefore 4 integral over dk nk divided by epsilon k minus q minus epsilon k. Now I continue here. Epsilon k minus q minus epsilon k. Here, for calculations, I will use parabolic dispersion. Namely, my spectrum is k squared over 2m. So this is k minus q squared over 2m minus k squared over 2m. I open brackets and I obtain k squared over 2m cancels out. I get q squared over 2m minus k times q divided by m. So this is my denominator. So therefore I continue that p q0 is equal to 4 integral k squared dk over 2 pi cube times integral from 0 to pi d theta integral from 0 to 2 pi d pi. I have nk, this is Fermi distribution function, divided by q squared over 2m minus k times q divided to m times cosine theta. This is my scalar product. So nothing depends on phi, but I first need to integrate over angles, and second, I need to integrate over modulus. So this is 0 to infinity. Okay? So I have 4 times 1 over 8 pi cube. Then I have a 2 pi coming out of integration over phi. I do the same trick, namely I denote cosine theta as x. Therefore, I have integral from 0 to infinity k squared dk times integral from -1 to 1 dx q squared over 2m minus k q over m x. Okay? I will take q squared k q over m out. So I have 4, 2, 8. 1 over pi squared. I take m over q. I multiply numerator and denominator by m divided by kq. I have integral from 0 to infinity k dk, because 1 power of k cancels out. And I have integral from -1 to 1 dx. Here I have 1 over q over 2k minus x. Okay? Everything is exact. Are you with me? Do you follow what I'm doing? Or you're lost? Do you hear me?
Hello?
Do you hear me?
Yes. Hello?
I do exact calculations of the polarization at zero temperature with the Fermi distribution function, which is step function. So this is Fermi distribution function, nk. Okay? So since it's nk, this integral, this gives me a logarithm. So I have m divided by pi squared q times integral from 0 to kf. Because of Fermi distribution function, I have k dk, and this integral is log 1 plus q over 2k, 1 minus q divided by 2k. Okay? So the remaining integral is just one-dimensional integral, which I'm going to compute. In principle, I plan to do it in all details, but we spend some time how to compute this integral. You integrate it by part. So you say that this is u, this is dv. Therefore, you write it as a uv minus v du, and this is a way to compute this integral exactly. I give you the answer. It will take me 1 page of doing calculations. So minus p as a function u0 is equal to m kf divided by pi squared times 1/2. And here there is a function 1 plus 1 minus q over 2kf squared divided by 2q over 2kf. And here there is a log 1 plus q over 2kf, 1 minus q over 2kf. So this is called Linhart function. Again, this is exact form of static polarization. We define the Dielectric function h as a function of z as 1/2 1 plus 1 minus z squared over 2z log 1 plus z 1 minus z, where z is equal to q divided by 2kf. I said that these calculations do not refer to any smallness of q. Actually, I did not assume it anywhere. But in particular, it refers also to small q. So the coefficient in front of the Linhart function is nothing but density of states. This is the density of states at Fermi energy. Let's plot this Linhart function as a function of q divided by 2kf. First of all, if q is small, namely z is small, we expand this. It's 1 minus z squared divided by 2z. Here, log 1 plus z divided by 1 minus z. It's z plus 2/3 2z plus 2/3 z cubed. All even terms cancel out, all odd terms collect. So you see that I take 2z in front. H at z goes to 0. This is z. Goes to 1. This is h z. You learned in your mathematical technique how to plot function. Then I have z over kf equal to 1. There is a special point. And let me shape how this function looks like. First of all, I discovered that for small z, it is equal to 1. You can expand and you will get that it's 1 minus some coefficient times z squared. So it goes down. Second, for this is z goes to 0. For z goes to infinity, I can rewrite this logarithm divided by z, numerator and denominator divided by z. It's equally applicable as log 1 plus 1 over z divided by 1 minus 1 over z. And do the same expansion, assuming 1 over z small parameter. If you do this expansion, you will get that this is proportional to 1 over z squared. So there is a tail 1 over z squared. So you already see that this function is monotonous. There is something which is happening with it at the argument equal to 1, because function has some peculiarity at z equal to 1. You see logarithm diverges. However, there is a coefficient in front of the logarithm which tends to 0. Therefore, if you use your knowledge which you learned in the methods of calculus, you analyze derivatives, you analyze how this function looks like, you see that at z equal to 1, there is an inflection point. Well, I'm a bit exaggerating. Actually, the derivative goes to infinity. And this is 1/2. So this is how linear function of z looks like for arbitrary argument. Okay, let's first understand what happens at small q. Because z is proportional to q. We plug it in here, so epsilon q0 is equal to 1 plus e squared divided by q squared times mpf over pi squared. And that's it, because for small q, the function approaches 1. So the dielectric function is 1 plus kappa squared over q squared, where kappa squared, again, I can do the same. I can rewrite Fermi momentum in terms of the density, and kappa squared is equal to 6 pi e squared density of electrons divided by Fermi energy. This is another very important shape of the dielectric function. You see the dielectric function diverges at small q. Not like in dielectrics. In dielectrics, dielectric function remains a constant. For metals, dielectric function diverges at small q. What does it mean physically? What kind of physical consequences it has? The effective interaction is equal to V naught, static effective interaction, Q0. V naught Q divided by epsilon Q0. I plug in this epsilon, so this is 4 pi e squared over q squared divided by q squared, 1 plus kappa squared over q squared. It's equal to 4 pi e squared over q squared plus kappa squared. So you see, instead of 1 over q squared singularity over Coulomb potential, we get screening. So our potential, effective potential, is no more singular. If you take a Fourier transform of this, so Fourier transform over V naught this one, is E square over R. So this is how we got our long-range interaction, right? Now, if we take a Fourier transform over this potential, what you get is E squared over R, e to the power minus kappa R. So you have your cover potential, which has exponential, not 1 over R tail, which means you screened your singularity of Coulomb interaction. 1 over kappa is the screening radius, which is called Debye radius, by the way, which is 1 over kappa. This is square root over Fermi energy divided by 6 pi e squared times electron density. So you see that Coulomb interaction is screened on the distances bigger than the Debye radius. And this is the second property associated with the property of dielectric function. Okay? Good. Now, before I do my last comment in remaining 2 minutes, what I suggest you to do in the homework. Compute Linhart function static polarization period. Is a function of Q at 2-dimensional case. You repeat the same calculations, assuming that you have a field. You only need to do proper integration over angle, but repeat it and see how this Linhart function looks like for 2-dimensional situation. I just plot it, it behaves like that. So it has Q. Compute it also, so problem number 1. This is what I'm listing.
What's the name of the function, Professor?
Sorry?
What's the name of the function?
Linhart function. Linhart function. I computed it for 3-dimensional case. So P, Q, 0, 2D, 1D. Then take your Linhart function and compute Fourier transform, so problems. This is problem number 1. Problem number 2. Fourier transform over Linhart function at 3D, 2D, and 1D. I will give you result for 3-dimensional case. Again, the calculations can be done exactly. You just need to practice in computing of the integrals. So for 3D, this Fourier transform is given by, so this is minus 8pf cubed over 4 pi, and here you have function cosine 2pf r divided by 2pf r cubed minus sinus 2pf r divided by 2pf r to the power 4. So if you plot it, it behaves as 1 over r for small r, and it behaves as 1 over r cubed for large r. And this function is oscillatory. What is interesting about this function is, first of all, it means, these oscillations are related to the inflection point or kink. So for 1D, by the way, the function will be divergent at 2kf. So this is 1D, this is 2D, this is 3D. But all functions have certain peculiarity at momentum transfer equal to 2k. So when you are on the diameter of your Fermi sphere. The singularity or peculiarity of this function relates to oscillatory behavior of its Fourier transform at any dimension, a plot three-dimensional case. It means that if you put impurity, charged impurity, inside of a neutral Coulomb system consisting of ions and electrons, what you will get? You will get certain oscillations of the density in your system. These oscillations are called Friedel oscillations. We come back to this form of this function in the magnetism, because in magnetism we will see that the response function density and spin are the same above certain temperatures, and therefore the correlation functions which I compute today will be also very important for discussion of the magnetism or stoner magnetism of the electron gas subject to some attractive, say, interaction. And we will come back to discussion of these oscillations, which in the theory of magnetism are known as Ruderman-Kittel-Kasue-Yasuda interaction, or RKKY interaction. Okay, that's all for today. I'm sorry that I started 3 minutes late because of the problem with Zoom in this room. Any questions?
I have a question.
Yes, please.
So, so even after
Can you speak louder because I cannot hear you well?
So there's going to be always a discontinuity in the average number at k equals k Fermi.
First of all, who is speaking? I don't see you.
It's me, Rolando.
Who? Sorry, please repeat.
Rolando.
Ah, Rolando. Okay. Your question is, are there always singularity of the at to kf or what? Please repeat your question.
Yeah, because I mean there appears that there is a discontinuity that at k equals the Fermi momentum.
Twice a Fermi momentum.
So
not a Fermi momentum, but twice a Fermi momentum, because it's Q divided by 2kF, and 1 corresponds to Q equal to twice the Fermi momentum.
Oh, okay.
Yes.
Okay, that's it. Thanks.
Yeah. It's related to formation of charge or spin density waves, as we see in the presence of interaction, some interaction, and in 3 dimension there is some threshold, and 2 dimension. In 1 dimension, it actually results that any 1-dimensional system is subject to all sorts of instabilities: spin density wave, charge density wave, superconductivity. And this is yet another reason to say that fermionic language for 1-dimensional system is not appropriate. One needs to adopt completely different language and completely different dictionary, which is a language of bosonization. In 1-dimensional, this Linhart function is logarithmically divergent at q equal to 2k.
Okay, got it. Thanks.
Okay, more questions? As I said, Andrei will rediscuss with you on Friday thermodynamics, computations of integrals with the Fermi distribution functions at finite temperature and quasi-particles in the Fermi liquid. If you have some questions which you already accumulated, please send it to me and Andrei, then we will have our tutorial in more efficient way. You should not be scared that I'm saying I finished the first chapter. The division of my lectures to the chapters is very relative. I mean, we will be back and back to certain parts. within the theory of magnetism, within the theory of superconductivity, and even with the theory of Bose-gas. So all lectures of the course are interrelated, and if you feel that you missed something, it doesn't mean at all that you will be completely blocked and stopped and you will be, say, screened from understanding everything else. Not at all. On Monday, we start with a discussion of Bose-gas, again, in a similar spirit. Namely, we start with non-interacting bosons, discuss boson state condensation, which occurs in the system of non-interacting bosons. We discuss thermodynamics of non-interacting bosons. Then we come to weakly interacting bosons. We see the Goldstone mode and we see how Goldstone theorem works. Then, based on this Goldstone theorem, we discussed superfluidity, one of the interesting and new collective properties in the system of weakly interacting bosons. And then we see how these weakly interacting bosons, and in principle fermions as well, can be studied in terms of ultra-cold gases being either in optical lattices or in harmonic traps. And then we come to superconductivity and magnetism. So, but you need to do a lot of work. So first of all, I suggest that you go through the calculations, you repeat each and every step. And if you have a feeling that you don't understand something, please go to the books. I gave you literature. If you still have a problem with understanding, please go to your tutor, which is the second person who is in a line to help you to understand. If you still have problems, please contact me and we discuss. Either if the question will be of general interest, so everybody is stuck in doing this, we devote some extra tutorial or whatever to discuss this question. If this is just particular question for you, we discuss just two of us. But before coming to me, please, first of all, try to do your best in order to understand yourself. Because one of the goals of this course is to teach you how to work independently. So at the end of the program, many of you will become PhD students, which means you start your own career as a scientist, as a researcher, and therefore one of the objectives of the course is to train you to work independently. The second objective is to work in a team. Therefore, you come to your colleagues, you discuss it collectively, you come to your friends, you come to your tutor, your junior colleague, and discuss with them. You come to your senior colleague, do it, but there is a lot of work to be done by you. I'm not going to do everything on the blackboard. I leave many details of the calculations to be done by you.
Professor?
Yes?
I don't know whether this is appropriate to ask, but can you please list all the suggested homework you give us before, and yeah, because sometimes you just suggest it and we don't really know what to write. So,
well, as I said, each and every lecture, I will suggest you to do something. For example, with the density, on a lecture when we discuss density of states, I said do it for 2-dimensional and 1-dimensional. Today, I gave you 2 types of problem, and in addition, proceed with a calculation of inverse lifetime, also in 3-dimension first. If you like, I can put this problem after each lecture as a file and send file to you. This is possible.
Yes, please kindly do that if you don't mind.
Please give me some time. I will also retrospectively come back to my previous lectures, these Gentile statistics, but again, this you will get official homework, and official homework will be given to everybody, will be evaluated, discussed, and this is something which is mandatory. So homework is a part of the business. But in addition to homework, I give you some problem to attract your attention. I'm not going to check that. I'm just going to sort of excite you or motivate you to work. And this is, by the way, one of the ways a scientist work. They become curious about something. For example, they know something, the behavior of some correlation function, and they start to think, well, there is related correlation function. It's interesting how it behaves. It's interesting because it can be measured, because it can lead to some new properties. It can be suggested to be measured. There are many different reasons and many motivations to do it. And then being curious is very important driving force for doing research. And one of the goals of my lecture is also to sort of say motivate you to ask question to yourself, not question to me. But as soon as you start asking questions, well, it's interesting, but it's not clear for me how this and that behaves. So as soon as you start asking questions yourself, you start to do some calculations by yourself. And in many cases, by doing calculation, you come to something which nobody yet discussed widely, or you are not aware about this discussion. So you come to your colleagues, you tell the result, they tell you that this is new and interesting, and then you write a paper. Of course, there are some other ways to do research. In principle, you can collaborate with experimentalists. They tell you that they observe some experimental puzzle and they want you to explain it. Or you have some mathematical problem which you want to resolve, and you see how this mathematical problem is related to some exactly solvable model. I'm not saying that there is a unique way to do research. Everybody will find his or her way to do it. And we are all different. We are all having different approach to things. Just choose what is more appropriate and interesting to you. We have whole diversity of ways to do research. And don't think if you are more experienced to set problem, or you are more experienced to do exact calculations, or you are more experienced to do interpretation of calculations, all this is good. I mean, just try to find what is more interesting for you to be excited and do it. And then you work in a team, the best possible team, when people with different skills meet. Some people are very strong in doing calculations, some people are very strong in interpreting results, and this is the best possible situation. Yeah. And you become independent researcher. Okay. Some more questions? With problems, Valerius, I will do it, so don't expect that I will do it today, because there are some duties which are on the top of my desk. But before end of this week, I will do it. Please don't forget that today, this Abdus Salam Memorial Lecture start. I think for you, participation in this Abdus Salam lectures is mandatory, because this is also part of your education. These lectures are given by one of world-leading expert. Even if you feel that this is very much detached or far away from your interest, it's very important to have a broad horizon and to be knowledgeable in different fields of modern theoretical physics. Having narrow expertise is never an excellent idea. Of course, you need to expertise and develop your excellence in some direction, but on the same side, you also need to be broad. So therefore, learning things from the first hand of leading world expert is a very good idea. And on Friday, there will be Dirac medal ceremony. Again, these three gentlemen are awarded for their work in cosmology. It's also mandatory for you, I think, to participate and attend the award lecture talks. They're going to be very interesting. So please do it. Please don't skip it. Please don't consider it as a facultative for you. I remind this is a mandatory. For those who did not register for this talk, please go and do it. Okay? And please send me questions, me and Andrei. And maybe we will have this style: 5 lectures, tutorial, starting new chapter, 5 lectures, tutorial, and so on and so forth. 4 chapters will mean 20 lectures and 4 tutorials. And altogether, 24 meetings. Okay. If that's all, we are done. You have time for lunch. I think you need to be hurried. Sorry that we are discussing longer, but this, when I say the lecture is finished, it means finished. I don't keep anybody. You can disconnect and do it whatever you like. But for those who would like to have extra discussion, you are welcome to. I'm ready to stay. I'm delighted to stay and answer your question. But we first need to finish say, necessary part of the lecture, and then we are continuing discussing some other things. But you are free, of course. Please feel free to disconnect and proceed. Okay, thank you very much. And believe me, I made these lectures deliberately tough because this is a part of education. The life and research is not easy. And you need to be prepared that not everything is explained on a blackboard. What is important to explain physics. Mathematics can be achieved by your exercising. But we are not going just to chat, see nice movies, nice slides. We are about to do calculations, and we are about to make a physical interpretation of what we have calculated. Okay, Pelush, you asked me a question. In principle, we can discuss it right away because I think that I need to understand your question and maybe need to take some time to find if I can answer it or not. Or we can do it after Salam lectures because you probably go to lunch now. I need to drive home at some moment. And how would you prefer to proceed?
Okay, let me, I'm going to send you an email containing my work where I need.
But I need to know if you want to discuss. So my understanding, you want to discuss it after Salam lecture.
Yes,
Something
yes.
like at 5 or between 5 and 6. Okay.
Yes. Okay.
Okay, thank you. Bye.